Hi all, welcome to lecture number 9 on PSW of 8051. PSW or Program Status Word or Flag Register is the most frequently asked question in university exams. So this is very important in the exam point of view. So we will start. We will first go through the overview of the register, then we will explain each and every flag in detail. So 8051's PSW Program Status Word is also called flag register, and it is 8-bit wide and its RAM address is D0H. Now it has 4 math flags in it. Math flag is the outcome of mathematical instruction. It is automatically set to the outcome of mathematical operation like addition, subtraction, etc. So we have 4 math flag. They are carry flag, C, auxiliary carry flag, AC, overflow flag, OV, and parity flag, P. Now we have one user programmable flag which can be set or resetted by the user, that is F0. So the programmer can use this flag to record some events in the program. Then we have 2 flags for register bank selection. I have already told you that we have 4 banks in the internal RAM of 8051. So for selecting 4 banks, we have 2 bits in our flag register. They are RS1 and RS0. They are the 4th bit and 3rd bit in PSW. Okay, so these are the bits available in our program status word. This is the structure of our program status word. As you can see, it has 8 bits, 0 to 7. While studying PSW, this position is very important. The position of each flag is very important. So we can first start from the 0th bit. The 0th position is for parity. Then the first position is not used. Then second position is overflow flag. Then third and fourth is the register selection bits. Okay, we have 2 bits. We are using this to select the register bank. So this is the combinations. If 0 0 RS1 is 0 and RS0 is 0 means bank 0 is selected, and this is the default bank. 0 1 bank 1, 1 0 bank 2, and 1 1 bank 3. Coming to the parity flag, the main register where the result of an operation is stored is our accumulator. The accumulator is an 8-bit register. If number of ones in accumulator is odd, then the parity flag is set to 1. If number of ones in accumulator is even, then parity flag is automatically set to 0. Now we will explain what is carry flag and when the carry flag is set. So carry flag is used in arithmetic, jump, rotate, and Boolean operation. So here you should understand the point when carry flag is set and why carry flag is used. So through a small example, I will explain to you that point. As you all know, 8051 is a 8-bit processor or 8-bit system. So 8-bit means all registers are of 8-bit. So I am just writing an instruction, add A, R0. So this instruction will add the 8-bit value in A and 8-bit value in R0 and store the result into A. That is A plus R0 is stored into A. And the result is also 8-bit. But in some cases, the result is more than 8-bit. Sometimes it will be of 9 bits. Then The extra bit we cannot store in accumulator because it is only 8-bit wide. So the extra bit is stored in carry flag. Let's see. So here we have 8-bit register. Suppose this is an 8-bit register. This is the 8-bit register. Now you should understand that what is the maximum positive number we can store in an 8-bit register. We are not dealing with signed arithmetic here. We are only dealing with positive numbers. So the range is the positive number. The range of positive number is 0 to 2 raised to n minus 1, where n is number of bits. What is the number of bits? 8. So the range is 0 to 2 raised to 8 minus 1, which is nothing but 0 to 255. So 255 is the maximum number we can represent with 8 bits. Anything greater than 255 cannot be represented with 8 bit. So in that case, we need some additional bits. Now let us consider the value in A is 255, which is the maximum value. 255 is nothing but 8 ones in binary. This is the decimal representation. This is the binary representation, and the hexadecimal representation is start from LSB, move towards MSB, group for 4 bits. So this is the first 4 bit, this is the second 4 bit. 1111 is nothing but F15, and this 1111 is nothing but F. So this is a FFH is a hexadecimal representation. So this is the hexadecimal representation. The processor will always function in binary format. So it will take this representation and add. Then in R0, I am taking 1. This is decimal. What is the binary value of 1? 8-bit binary value is this is binary, and for hex 0001 is nothing but 1, and this is 0. So 01H, this is hex. So we are going to add these two numbers. We all know that 255 plus 1, 256 is bigger than our range. So the result cannot be stored in accumulator. So we are going to add these two numbers, 1111 0000 1 plus 1 2, right? 2 means 0, 1 0 is 2, so 0 and 1 is carry. 1 plus 1 0, 1 plus 1 0, carry 1, 1 plus 1 0, carry 1, carry 1, 1 plus 1 0, and there is a carry. There is a carry from this bit, which is 1, and this carry cannot be stored in accumulator, right? Because accumulator, this is stored in accumulator. This is already 8-bit. This is stored in accumulator, and this 1 is stored in our carry flag. So this one, or the 9th sorry, we are always starting from 0. So this is the 7th bit and this is the 8th bit. So the 8th bit, which is coming as a result of addition, is stored in carry flag. So this is the use of carry. So after this instruction is performed, our accumulator has a value 0 0 0 0 0 0 0 0 and the carry flag has a value 1. This carry flag cannot be discarded because the carry flag is a MSB of our result. Why carry flag is MSB? Let's see. So you all know the weights in binary system, right? Binary system, the weights start from 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7 and 2 raised to 8. I am taking here 2 raised to 8 till 2 raised to 8 because how many bits are here? 9 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this is nothing but 1, 2, 4, 8, 16, 32, 64, 128, 256. So our result after addition is what? 255 plus 1 is 256. This is the 256. This is the representation of 256 in binary because here we have weight 256, right? So beneath that weight we are putting 1 and rest we are putting zeros. So this is a representation of 256 and this much part of our result is stored in which register? Accumulator, and the extra bit is stored in carry flag. So the carry flag cannot be discarded because carry flag is actually MSB of our result. So this is the significance of carry flag. Now coming to overflow flag. So overflow flag is used in signed arithmetics. Signed arithmetics means when dealing with negative and positive numbers. When we are dealing with only positive numbers, that is unsigned arithmetics, we are not using this flag. This flag is of no importance. But in signed arithmetics, this flag is of importance. So we will see when the flag is set in signed arithmetics. As you have already seen, the range of positive number in 8051 is, we already know 8051 is a 8-bit processor, right? So the range is 0 to 2 raised to 8 minus 1, that is 0 to 255. This is the maximum positive number we can store in a register of 8051 if we are using unsigned arithmetics. But for signed arithmetics, the range is different. Signed arithmetics range, because in signed arithmetics we are dealing with both negative and positive number. So the range is, the formula is minus 2 raised to n minus 1 to, in the positive side, the formula is 2 raised to n minus 1 minus 1. So this is the range. So for n, if you are substituting 8, for n equal to 8, 2 raised to n minus 1, 8 minus 1, 7, to 2 raised to 7 minus 1. So the range is minus 128 to plus 127. So here notice that we will get one extra negative number. So this is the range. And another thing is that In signed arithmetics, the leftmost bit, that is the MSB bit, is actually the sign bit. It is not actually used to define the magnitude, but it is used to define the sign. Example, if this is a number, consider this number in signed arithmetics. This is a sign bit. This bit is already considered or always considered as sign bit. This bit is not for the magnitude, but it is for showing the sign. If it is 1, this number is negative. If it is 2, if it is 0, the number is positive. So here this is a negative number. So this is sign bit. Keep that in mind. So we are going to perform an addition. Our maximum positive number is 127, right? So we are going to perform 127 plus 1. Result is 128. But this 128 cannot be represented in our signed arithmetics. So let's see in binary form. 127 can be written as, this is positive 127, right? So the sign bit is 0. Then 127 means the rest of all are 1s. Okay, this is positive 127 in signed arithmetics. Then positive 1. For positive 1, here 0. Rest all are 0. Here a 1. So this is positive 127. This is positive 1. Okay, let's add this. 1 plus 1, 0. 1 is a carry. Again, 1 plus 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then a carry here, 1. So 1 plus 0 plus 0, 1. Now notice that in our result, our sign bit is changed. If we add two positive number, the result should be positive, but here we are getting a negative number. This is the case of overflow because we are out of the range and we cannot represent positive 128 in signed arithmetics. Under this condition, our sign bit is changed. So when the sign bit changes, the overflow flag is set. So when the overflow flag is set, we should know that we are out of the range from our prescribed range, that is positive 127. Okay, so the overflow flag is used in which arithmetics? Signed arithmetics only. And if the sign bit changes, the overflow flag is set. So under this condition, the overflow flag will be 1. And this indicates that we are out of the range. Or in other words, we can say that the magnitude of the result of this addition has overflowed into the sign bit. This is the condition where overflow flag is set. Now we will see auxiliary carry flag. Actually, auxiliary carry flag is used in decimal arithmetics or BCD arithmetics. Okay, this decimal arithmetics is also called BCD arithmetics. So in decimal arithmetics, in a decimal system, we have numbers from 0 to 9. And each number is represented in its corresponding 4-bit binary number. So you already know how to represent the number in 4-bit binary number, right? We have seen in our hexadecimal video. So 0 means 0, 0, 0, 0. Then we have 1, 0, 0, 0, 1. Then 2, 0, 0, 1, 0. Then 3, 0, 0, 1, 1. 0, 1, 0, 0. 0 1 0 1 0 1 1 0 0 1 1 1, then 1 0 0 0 and 9. So this is the representation. Now actually in 4-bit representation we can write up to 15. So rest of the numbers are so in BCD system these are unused numbers. They are not used because we only have digit up to 9. So this is unused. Even though we can write up to 15, we are not using these numbers in 4-bit representation. So in BCD arithmetics, now we will see how the auxiliary carry is used. So we will perform a simple addition. We will perform addition on 49, 38. So adding this, we will get 87, right? This is in decimal. So in our microcontroller, we are going to convert 49 to its equivalent BCD representation and 38 to equivalent BCD representation and adding. So 49 for 4 we are substituting, for 4 we are using this 0 1 0 0, and for 9 we are substituting this 1 0 0 1. Okay. Then plus for 38 for 3 we are substituting this 0 0 1 1, and for 8 we are substituting this 1 0 0 0. Okay, now we are adding. So this is the BCD representation. Remember that this is not binary representation, this is BCD representation. So here it is 1 0 0 1 plus 1 is 0, carry 1. So here is a carry generated from this bit to this bit, this carry, and this carry is actually the auxiliary carry. So the carry generated from 3rd bit to 4th bit is the auxiliary carry. Third in the sense that we are starting from 0, right? 0 1 2 3. This bit is the 3rd bit to 4th bit. So 3rd bit to 4th bit, if the carry is generated, then it is an auxiliary carry. And if the carry is generated means this result is wrong. We can see here redly, right? Because we want to get 7 here, but we are getting here 1. 1's equivalent is this thing. We are getting 1. So we want to correct this addition. So okay, we will correct it, but we will complete the addition. So a carry is generated to this bit. So 1 plus 1 is again 0, then 1, 1 plus 1 0 1, 1 plus 1 0, then 1, 1 plus 0 plus 0 1. Here is correct. This 4 bit is correct, right? This is the representation for 8. Here we can see that, but this is not correct. So to correct this, the general rule is that in BCD addition, if one number is not correct, we are adding 6 to it. 6 it is the general rule. Okay, so we are adding equivalent of 6. Equivalent of 6 is 0 1 1 0. So here only we are adding because this is correct. 0 1 1 0 6. Now we will see. Here it is 1. Here it is 1. Here it is 1. Here it is 0. Then 0 0 0 1. Now our result is correct. This is 8 and this is 7. Here see, this is representation of 7. So now our result is correct. So for this correcting factor, we are adding 6. So this is the use of auxiliary carry. If an auxiliary carry is generated, then our result is correct. Result is not correct. So we want to add 6 to make our result correct. And this carry is actually stored in the auxiliary carry flag. So now we will see parity flag. So parity means number of ones in binary representation. If number of ones are odd, it is called odd parity, and if number of ones are even, it is called even parity. So in 8051, the parity flag shows the parity of the accumulator. So as we know, accumulator is 8-bit. This is our accumulator, which is also called as a register, which is 8-bit. Let us consider for the time being, this is the bit pattern in accumulator. So here, how many ones are there? 1, 2, 3. Odd number of ones, right? So this is odd parity. If odd parity, in case of odd parity, then the parity bit is set to 1. The parity bit or parity flag in PSW is set to 1. And in odd parity, in case of odd parity, in case of odd parity, and this is example 2. In this case, how many ones are there? 1, 2, 3, 4. So parity is even. So in even parity, the parity flag is set to 0. Even parity. The parity flag is actually used in serial communication to check the correctness of the received data. So next we will see how to use PSW in programming. So this is our PSW, which is of 8-bit. PSW is both bit addressable and byte addressable. That means each and every bit can be set individually, or a 8-bit number can be directly moved to PSW. That is meant by byte addressable. So we can use either move instruction or boolean instruction like set bit instruction or clear instruction to set or clear specified bit in PSW. So by move instruction, if in our program, if we want to have PSW to be filled with certain values, then we can move that value into the PSW. Like for example, if we move PSW comma in immediate addressing mode, hash shows it is immediate addressing mode 00H. So after this instruction is executed, our PSW is loaded with 8 zeros. So now the PSW will be like this. It is loaded with 8 zeros. Okay, so this is the state of PSW after this instruction is executed. Now I will ask you a question. Which bank is selected if the state of PSW is this? So bank selection bit are 4 and 3. 0, 1, 2, 3 and 4. So this is RS1 and this is RS2. So RS1 and RS2, RS1, RS2, not RS2, this is RS0. Okay, RS0. So the value is 0, 0, right? So 0, 0 means we have already seen at the starting of the lecture, 0, 0 means bank 0 is selected. So 0, 0, bank 0. Bank 0 is selected. And our carry flag has value 1, auxiliary carry. Carry flag has value 0, auxiliary carry has value 0, and rest all of the flags have value 0. So this is one way of using our PSW. The next way is using bit addressable instruction. So I will write this instruction: set b PSW dot 4 set b PSW dot 3. So this is the instruction. So the fourth bit is set to 1 and third bit is also set to 1. Rest of the bit has some random value. So after executing this instruction, our PSW will be like this. Fourth bit is set to 1 and third bit is also set to 1. Rest of the bit has some random value. Let's assume some random value like this. So under this condition, which bank is selected? RS1, RS0. Both are 1 means bank 3. So like this, we can set and reset each and every bit in PSW, either as byte addressable or as bit addressable. Then I will show other instruction. If you want to clear a bit, if you want to clear this bit, we can say clear PSW dot 4. So this bit will be made 0. So now I am concluding this lecture on PSW. I will give detailed notes in the description. So please comment in the comment section how you feel about this video and consider subscribing to this channel.